Hello students, in this video we'll be further extending our understanding of the topic of chemical equilibrium through the following learning objectives. You may just pause the video here for a minute to go through these learning objectives and then proceed. Alright, so let's start with the first learning objective, which has to do with equilibrium law. So let's start with a hypothetical reversible reaction, which is A moles of A plus B moles of B gives C moles of C plus D moles of D. So here, clearly, the uppercase A and B are our reactants, and the uppercase C and D are our products. And all the lowercase letters that you see here are stoichiometric coefficients that we use for balancing a chemical equation. So what does this law state? This law states that the ratio of product to reactant concentration with each term raised to the power of their stoichiometric coefficient is a constant as long as the temperature is constant, and that ratio is called equilibrium constant. So what does the statement look like mathematically in this context of this equation? So K equals, so we first write the product concentration, which is C within a square bracket, raised to the power of its stoichiometric coefficient, which is the lowercase c, times the molar concentration of the product, the other product here, raised to the power of its stoichiometric coefficient over molar concentration of A, which is our first reactant, raised to the power of its stoichiometric coefficient, times molar concentration of B raised to the power of its stoichiometric coefficient. So what this law states that at equilibrium at a given temperature, the ratio of the product to the reactant concentrations, because each of them has become a constant, so the ratio of these concentrations is also going to be a constant, and that constant is called equilibrium constant, symbolized by capital K. A very important difference, capital K is quite distinct from the small k, which we'll use for rate constants, especially for the HL students. So again, this kind of implies the same thing. If you have this particular hypothetical equation, this is the expression for equilibrium constant. The important thing to know is that you need to only have the concentrations of products and reactants at equilibrium. So this ratio can be measured anytime, right? You can measure the product and the reactant concentration at any time, but it will be called equilibrium constant only when you measure them at equilibrium, right? So again, this slide kind of makes clear what each term signifies. We may just pause the video here for a minute to understand what it means. All right. So let's now try writing the expression of equilibrium constant for different homogeneous reactions. So reactions where the phases of all the reactants and products is going to be the same. So for example, here we have a gas phase reaction. Nitrogen in the gaseous state is reacting with hydrogen in the gaseous state, making ammonia, and this is a balanced chemical equation. So how do we write the equilibrium constant K for this particular equation? So that will be product concentration, which is ammonia over here. We'll write ammonia within the square bracket, and because the coefficient is 2, this is raised to the power 2 over the reactant concentration, which the first reactant is nitrogen, and since the coefficient is 1, we don't need to put anything here because this means raised to the power 1 times the molar concentration of hydrogen raised to the power 3 because the coefficient is 3. So now if you have understood how to write expressions for equilibrium constant, I'll like you to try to write the expressions for equilibrium constant for all of these three reversible reactions. You may just pause the video and proceed further once you have attempted to write the equilibrium constant expressions for all these three equations. Alright, so here are the answers. In case any of the answer contradicts your own answer, you may just approach me and clarify your doubt. Otherwise, this is a pretty straightforward um, concept. Now, uh, we know that one of the characteristics of chemical equilibrium is that it can be achieved from any direction. All right. So just to emphasize that the equilibrium constant does not depend on what the initial concentration of reactants and products were. Here we have 6 sample experiments which started with different concentrations of nitrogen, hydrogen, and ammonia. And as you can see, this is the expression for the equilibrium constant for this reaction. And in these 6 experiments, here were the concentrations at equilibrium. So what I need for you to do is to use this expression to calculate the value of equilibrium constant in all these 6 experiments. And then I would like you to pause the video and deduce what conclusion can you draw from these 6 experimental observations. So as you may have calculated yourself, the value of equilibrium constant comes out to be C. You may also be making one more observation here that equilibrium constant does not have any units. That's because in the real sense, they don't actually take molar concentrations, but another thing called activities, which don't have any units. So if you take ratios of two quantities which don't have any units, clearly it won't also have any units. But just to make our life easier, um, you don't have to actually go about mentioning activities. Instead, stick with the term molar concentrations. So when we substitute the value of the molar concentrations of all the reactants and products in the 6 scenarios, you get the same value of equilibrium constant. So irrespective of what the initial concentrations were and what the final concentrations at equilibrium were, you see that the value comes out to be same as long as the temperature is same. That's because you know that if a reaction is endothermic, increasing the temperature will allow more product to form, increasing the value of equilibrium constant. Similarly, if a reaction is exothermic in nature, increasing the value of temperature might favor the backward reaction, so it would decrease the value of equilibrium constant. More about that in Le Chatelier's principle. But the idea that you need to keep in mind is that the value of equilibrium constant does not depend on what the initial concentrations were. It only depends on the ratio of the molar concentrations of products and the reactants at equilibrium and at what temperature it was carried out. Now comes the last part of this tutorial, which is to understand the significance of equilibrium constant. So equilibrium constant is actually closely aligned with thermodynamics. Basically, it kind of reveals to what extent is the reaction proceeding in the forward or the reverse direction. So again, you know that equilibrium constant is, loosely speaking, the ratio of product concentration over reactant concentration. We are kind of ignoring the coefficients for the time being just to paint a very simplistic picture. But this is what basically equilibrium constant is. Now imagine this value being very large. Now what would that mean? It would mean that at equilibrium you have very large amount of product compared to reactant. So what does that mean? It means that this reaction is a product dominated equilibrium. Another way to basically put this is that here the equilibrium lies to the right, or the equilibrium favors the product formation. Similarly, if the value of equilibrium constant is very small, and when I say very small compared to 1, so it basically means there is more of reactant as compared to product. So this is a equilibrium which is dominated by reactant concentration. In other words, it is an equilibrium which lies to the left, or an equilibrium which favors reactants. So these are different ways to basically express the direction in which the equilibrium lies. So if you have a very high value of K, it means that you have more of product, so you say the equilibrium lies to the right. If you have a very small value of K, you say it's an equilibrium which lies to the left, and the equilibrium favors the reactant concentration. And the value of reference here is 1. So basically 1 would mean that you would have a similar or identical reactant and product concentration. And so you'll have very similar amounts of both of them. But a value of K which is extremely large compared to 1 means that the equilibrium lies to the right. And if it's a value which is very small compared to 1, that means the equilibrium lies to the left. Another thing that an equilibrium constant measures is also the um, comparative stability of the products that are formed in a reaction. For example, if we have these formation of three hydrogen halides which are all measured at the same temperature, these are the equilibrium constant values. So I want you to think for a minute, what do these values indicate about the extent of the reaction? And using the data booklet, can you relate the equilibrium constant values with the bond strength of these hydrogen halides? You may just pause the video here for a minute and then proceed ahead to verify your answers. So here we see that there is actually a direct correlation between the strength of the bond and the value of equilibrium constant. So because hydrogen chloride has a shorter bond length, it has a higher bond dissociation enthalpy, and that means it's a more stable product. As the result, you can see a very high value of equilibrium constant. You can see that the value equilibrium constant of Hi is the lowest. That's because compared to the other two hydrogen halides, the bond length is the highest, which means the bond enthalpy is the lowest, which means the product is not as stable as the other hydrogen halides. And you can see the hydrogen bromide lies somewhere between these two extremes. So here we have the bond length which is intermediate between the other two, and the same goes for its bond enthalpy. As a result, its thermodynamic stability is between the two extremes, and so does the value of equilibrium constant as well. So here you need to remember that equilibrium is a thermodynamic concept. Okay, so if the side to which it lies indicates the side that's more stable at that specific temperature. So if at 550 Kelvin, the equilibrium constant of hydrogen chloride is 10 raised to the power 18. That does tell you that at that specific temperature, the relative stability of hydrogen chloride is more than the relative stability of the reactants that it was formed, and that's why it has a high value of equilibrium constant. Do remember that just because equilibrium constant value is high doesn't necessarily mean that it's a faster reaction. We do need to keep in mind that um, rate of reaction and extent of reaction are two different things. Rate of reaction is determined by chemical kinetics, which is a different branch of chemistry, and the extent of reaction is determined by thermodynamics, which is again a different branch of chemistry. So I hope this tutorial has clarified the learning objectives. If you have any queries, please do reach out to me. Thank you so much.